All right, so here we want to look at solving rational equations. When we solve a rational equation, we're again going to use the least common denominator, although again slightly in a different way than if we were adding or subtracting or simplifying a complex fraction. Now, typically on a multiple choice test, you'll see things, let's say, solve the equation if no denominator is 0. And this is just there to remind us again that we have those restricted values which can produce what we call extraneous solutions, depending. So let's take a look at this first example. This first example, the math is actually relatively simple because the process I want to look at here is first looking at my denominators. I'm going to look at my denominators and determine a least common denominator. So if I have the denominators x, 6x, and 4x, then for my LCD, clearly I need an x. And then the question is, what do I do with the 6 and the 4? Well, I need something that is divisible by both 6 and 4. 6 and 4 have a common factor of 2, but 6 is 2 times 3, 4 is 2 times 2. Now, I'll leave it to you to figure this out. It's pretty simple, but 6 and 4, of course, both go into 12. So my least common denominator is 12x. Now, once I have my least common denominator, I know I can think about restricted values. Based on this, my least common denominator is 12x, or 12 times x. So the only restricted value I would get is that x cannot be 0. If x were 0, I'd have division by 0, which we know is not possible. It's not something that we can do. So what I'm going to do is take each of these different terms and multiply them by that least common denominator. So I'm going to rewrite this, and I'm going to leave myself some space to show that work. Now again, you've seen me do this before. I'll put parentheses around the numerator because if I'm going to multiply, I need to remind myself that it is in fact distribution that's going to happen here. Or in some other cases, we might have to multiply two binomials. So each of these is going to get multiplied by the least common denominator, 12x. And again, the reason that I do this is because it allows me to actually get rid of the denominators that I already have. With this first term, well, my denominator is x, so I can simplify the factor of x in 12x. With the second term, 12x and 6x, I can simplify the x, and I can simplify 6 and 12 and be left with 2. For 12x and 4x, I can simplify the x's, and 4 and 12 leaves me with 3. So, at that point, this is what I now have. 12 times 2x plus 1 minus 2 times x plus 9 is equal to 3 times 3 minus x. Now at that point, this has become a very, very simple equation. And the only thing that we really need to worry about is, of course, to be careful with distribution. Because the number one place where people can make mistakes here is with distributing a negative number. If you don't distribute the negative number, you can solve this and end up with a completely wrong answer and be none the wiser. So we'll go ahead and distribute and go ahead and solve this. If I combine like terms over here, I will have 22x minus 6 is equal to 9 minus 3x. And then what I want to do is get my x's to one side. If I add 3x to both sides, I will get 25x. If I add 6 to both sides, I will get equals 15. I combine two steps there at once, but again, you've been doing algebra long enough, you know what I'm doing, so you should be comfortable with that. So if I want to solve for x, I divide by 25. And I get that x is equal to 15 over 25. Well, 15 over 25, of course, simplifies to 3/5. I know that this solution is valid because it was not the one restricted value I had. I said that x could not be 0, and here it is not 0. So I don't have to worry about that. It's not 0, and this should be a valid solution. Now, a quick comment. Again, I'm trying to show you the math here. If you're doing this on a multiple choice test, something that might be useful to you is to know how to do this on your graphing calculator. So on your graphing calculator, you can use all sorts of interesting features. And I'll show you my graphing calculator right here. Okay. Now you see, I don't have any settings set up. I've just have my TI-84 Plus and everything's cleared out. And what I'm going to do is enter one side of this equation into y1 and the other side of the equation into y2. So these are rational expressions. You either have the choice of entering them in with an adequate number of parentheses, such as this, parentheses around the numerator, divided by parentheses around the denominator. And the same thing for the second expression. Be careful with those parentheses, though. And this is all well and good, and if you use enough parentheses, it'll certainly work. But a neat little feature that we have on the newer TI-84s is that if I hit alpha F1, I pull up this n over d, which will allow me to enter in a fraction as it is usually shown. So let's click that, alpha and F1, or alpha y equals. And I see here I have a fraction. Now, I can just type this in how it's shown to me. 2x plus 1 over x minus alpha F1 x plus 9 over 6x. Now, what do we do with the other side of this equation if we're trying to use a calculator to solve this? Well, you have a couple of options. You could actually subtract this over to the left-hand side and look for zeros, or your other option is to put it in as y2 and look for the intersection of these two graphs. I'm going to put it in as y2. 3 minus x over 4x, excuse me, I mistyped that. And I'll go to the graph and see what this looks like. Now these are rational functions, and their asymptotes are going to be the y-axis and other things. So we see right here, we don't get a very good look at that graph. We could zoom in if we needed to, but what I'm curious about is where they intersect. And I can see that they intersect at a point right in here. Okay, well, let's go to second calculate. And remember, we've done this before. If you find the intersection, option 5, it's going to ask you for your first curve and second curve. Well, the first curve will automatically be y1, and when I hit enter, oh, be careful here. I'm on x equals 0 and y is not defined, so the calculator is not going to let me choose this. So I'm going to move over so that I can see any y value. Then I can select this as my first curve. I'll hit enter. Now second curve. X and y are both defined here, so I can hit enter. And it asks me for a guess. For the guess, generally speaking, you don't usually have to move it, but if you do, you just want to get it close to whatever point you're interested in. Now it's very small. It looks like I'm close to that point. I'll go ahead and hit guess. And the calculator does its work and tells me the intersection is 0.6. The y here is 1, but remember, I didn't have an actual y value here. I only had one variable, so only this x value is interesting to me, not the y value. And I got 0.6. What's the significance of 0.6? Well, 0.6 is, of course, 3/5. Can you do this for every single problem? No, not really. Some questions might require you to type in your answer, and if the answer is something like 43 over 13, you're not going to be able to approximate that very well from a graph because 13ths are a very unusual pattern. But if you get a pattern that you recognize as thirds or any other pattern you might recognize, such as, say, ninths or 11ths, or if you get a terminating decimal, you can always go back to your calculator and say 0.6 and change it to fraction by hitting math to fraction. And it tells you it's 3/5. All right. So again, that's just a little side tip. I'm not going to focus on these tips. They're good to know, but for right now, I'm going to focus on doing the math. I'm going to go ahead and move on to a different example. I'm going to have several examples here, just giving you a good range of what you could encounter for these types of problems. All right, here's our second example. Again, take some time to write this down. You can pause or rewind as needed. What I need to do here again is figure out my least common denominator, which means I need to factor the denominators. D minus 3, as luck would have it, is already factored. 9, we know, has a factor of 1, a denominator of 1. So I'm not concerned with that. But what I do need to factor here is d squared plus 2d minus 15. All right. Well, the leading coefficient of that is 1, so I know it's d and d. The factors of negative 15 that add to positive 2 are positive 5 and negative 3. So I can see that the two denominators actually share a factor. So then, my LCD must be d plus 5 times d minus 3. Okay? So then, what do I know? What restrictions does that produce? Well, if I have d plus 5 equals 0, that will give me d is negative 5. And if I have d minus 3 equal to 0, that would give me a restriction of d equals 3. So those two are my restricted values. Now again, I'm going to follow the same exact process as I did in the previous problem. Rewrite each of these And again, I'll give myself some extra space. I'll make sure to put numerators in parentheses so that I don't screw anything up. I'll write the factored version of the denominator. Okay. Now, I'm going to multiply each of these by the LCD. Now you notice before I multiplied it on the left, here I'm multiplying it on the right. Absolutely no reason to that. It doesn't matter because we know that multiplication is commutative. I can multiply on either side and it is equivalent. Wrote over my equal sign there a little bit, sorry. Alright, again, the reason I'm doing this is it allows me to cancel out denominators. So here I'll be able to simplify d minus 3 and d minus 3. Here I'll be able to simplify both factors. And on the right-hand side, I will just have to multiply 9 and the two binomials d plus 5 and d minus 3. So what am I left with? I have 2d minus 11 times d plus 5 plus, this is now just 10d minus 70. Nothing was being multiplied by it. Both factors of the LCD got simplified. And on the right-hand side, 9 times d plus 5d minus 3. Well, you can multiply this out again, or if you remember, where did it come from? This was this original denominator. d squared plus 2d minus 15. Now again, this is not ultimately that hard of a problem. I just need to multiply stuff out and go ahead and solve. So let's multiply. If I multiply 2d minus 11 and 2d plus 5, you will end up getting 2d squared. Let's see, minus 11 plus 10 is minus d minus 55. Here I can just remove these parentheses and have 10d minus 70. Over here I will have 9d squared plus 18d minus 9 times 15 is 135. Alright. I combine my like terms over here and get 2d squared plus 9d minus 125 is the sum of those two. Now, what we see here very clearly is a quadratic. And if you learn nothing else in Algebra 2, you know that to solve a quadratic you have to have 0 on one side. So I'm going to move everything to one side of the equation. Which side? Well, if I move stuff over to the right side, I will have a positive leading coefficient for my polynomial. So let's do that. If I subtract 2d squared, I'll get 7d squared. If I subtract 9d, I will have plus 9d. And if I add 125, I will then have minus 10. Okay, so I have 0 is equal to 7d squared plus 9d minus 10. This is a polynomial I now need to factor. Alright, I'll show you the factoring on this one. Again, I may skip some steps as we move through this. 7d squared plus 9d minus 10. If I multiply these, that's negative 70d squared. Well, what are the factors of negative 70 that add up to 9? Again, you might want to think about this. It's not 7 and 10, we know that much. But the factors of 70 are 1 and 70, 2 and 35. Next up would be 5 and 14, and then 7 and 10. Well, again, it has to be negative 70, positive 9 means I need a negative and a positive number. So I can use 5 and 14. If I do plus 14d minus 5d, then I will get what I want. All right. So when you factor this, the GCF of the first pair is 7d, leaving me with d plus 2. The GCF of the second pair is negative 5, leaving us with d plus 2. All right. Now I've run out of room a little bit here, so I'm going to come over to the side. Forgive me for that. 0 is equal to 7d squared plus 9d minus 10, which we now know factors as d plus 2 times 7d minus 5. And it looks like I have two solutions here. I take each of these factors and set them to 0. If d plus 2 is equal to 0, I get d is negative 2. If 7d minus 5 is 0, then I get that d is equal to, I'll first add 5, then divide by 7, so that'll be 5/7. Okay, I got two solutions. Now again, something you must check. Are either of these extraneous? Well, the two possible extraneous solutions I got were negative 5 and 3. Those were my restrictions. These are neither of those. So this is an equation which has two actual solutions. My solutions are negative 2 and 5/7, or if I write that in the form of a solution set, I get negative 2 and 5/7. Okay? All right. So let's keep going. See some different examples. All right. This is based on a problem on a released SOL. This looks much simpler. Now, some people might gravitate towards cross-multiplying here, and you can. It's just that be aware if you do cross-multiply here, ultimately it's going to produce an extraneous solution that you really don't want to have. All right, let's look at the least common denominator here. Well, I've got y squared and I've got 2y. If I start off with y squared, because I need the higher power of y, well, what does this have that that doesn't? I already have a y, but I don't have a 2. So my least common denominator is 2y squared. So that's what I'm going to do, is I'm going to multiply both the left-hand side and the right-hand side by 2y squared. And then, again, the idea is to simplify what I can. Here, the y squareds will simplify. Here, I lose the 2. And y squared and y leaves me with just a single y. Okay, so what am I looking at now? I have simply 2 times 3y minus 4 is equal to 3y. Alright? Now, a quick comment here. I forgot to list our restrictions up here. Of course, if I have 2y squared, then my only restriction, if I set each of these to 0, 2 equals 0 gives me no solution. Y squared equals 0 gives me y equals 0. So that's my restriction. Y cannot actually be 0, because that would make the denominator 0. So let's go ahead and multiply this out and solve. 6y minus 8 is 3y. Subtract 6y from both sides, and negative 8 is equal to negative 3y. If I divide by negative 3, then y is equal to, I have a negative divided by a negative, y is 8/3. And thus I have solved it. Very simple problem, so long as, again, you understand what you're actually doing. And again, this I know is valid because it doesn't make the denominator 0. All right, so I'm going to keep moving along because I don't want to make this any longer than it needs to be. Let's take a look at another one. Another one that here cross multiplication is actually equivalent to what we're going to do regardless. My two denominators, you see, have no common factors, as opposed to our previous example where y was a common factor. So whether you think of this as cross multiplication or least common denominator, for this particular problem, since I just have one fraction equals another fraction, they will be equivalent processes. So my least common denominator, I need my first denominator and I need my second denominator, which is totally distinct. So I have 4 times n plus 5. All right, so let's go ahead and solve this. If I multiply by 4 times n plus 5 on both sides, what I will get is this. And actually here we see where cross multiplication actually comes from. It's really just basic algebra. Here the 4's can be simplified. Here the n plus 5, can be simplified. All right, what does that leave me with? I now have n plus 5 times 4n minus 3 is equal to 4 times n squared minus 5n. And once again, I've forgotten to list our restriction. So I feel like I should be chastised for that. N cannot equal negative 5. Shame, shame for not writing that. All right, so now we actually multiply this out. N plus 5 times 4n minus 3. Foil, box, do something to actually multiply this out. What you will get is 4n squared plus 20 minus 3 is plus 17n minus 15. Over here, I distribute and get 4n squared minus 20n. Well, this looks like I have a quadratic, except the very first thing I'm going to do is try and get everything to one side. When I subtract 4n squared, those will just be gone. And what I'll be left with instead is 17n minus 15 is equal to negative 20n. Okay, then what am I going to do? I'm going to subtract 17n to get the n's to one side. And then I'm going to divide. So what does that leave me with? This, of course, is 1. That's why I divided by negative 37. Negative 15 divided by negative 37, well, two negative numbers, again, their quotient is positive. So n is 15 over 37. So if you had tried to solve this with a calculator, if you needed to type in your answer, you probably would not have had much luck here. 15 over 37 is not a number that you're going to recognize just by looking at its decimal representation. The previous example, 8/3, you probably could have recognized that because you know that a third is 0.3 repeating, 2/3 is 0.6 repeating. So, again, ultimately, as I've said always, to do math, you have to actually know math. That's your best bet. All right, so we went through 4 examples there pretty quick, and these are all pretty simple. Now, the last one I'm going to show you, this will produce a quadratic, but something strange is going to happen, something that we have to remember to be careful with. Now, this looks very ugly when I first show it to you because there's a lot of squares, there's a lot of just everything staring you in the face. So again, my process here has got to be to find the least common denominator. I have q minus 7. I have 3q minus 4. Each of those are distinct factors. And then I see this polynomial over here, this quadratic. Well, hopefully, and the way these problems typically work out, that is going to be the product of these two particular binomials. I'm just going to spoil the surprise and tell you that it is in fact that. If you tried to multiply this, I would need factors of 3 times 28. 3 times 28 is 84. Factors of 84 that add to negative 25 are negative 21 and negative 4. Okay? So if you're factoring it long ways, that's what you would have to do. You'd have to do negative 21q minus 4q and then go from there. But I'll just spoil it for you and say that this is in fact 3q minus 4 times q minus 7. Alright, so then what's our least common denominator? Our least common denominator is, clearly, q minus 7, 3q minus 4, because those are the only two factors I see in any of the denominators. What restrictions does this give me? Well, that means that q certainly cannot equal 7. And if I solve this right here, if I set it equal to 0 and solve it, that would produce a root of 4/3. So those are my two restrictions. Q should not be 7, it should not be 4/3. So again, what's my process? I'm going to take each of these three things, write them again, and multiply by the least common denominator. I'll give myself some room to do that. I'll do it on the left because that's where we most commonly see things being multiplied. But as I said before, multiplication is commutative, so you could do it on the right just as easily. And again, I will write the factored version of this denominator rather than its actual product. All right, so I'm multiplying by the LCD. The LCD is q minus 7 times 3q minus 4. Over here, q minus 7, 3q minus 4. I should have left myself a little bit of room there. Sorry, that looks a little bit messy. Over here, I'll try and write this a little bit neater. 3q minus 4 and q minus 7. And again, I changed the order. I apologize. Nothing intentional there. We know multiplication is commutative, so the order of those two factors does not actually matter. All right. So this allows me to eliminate denominators. Q minus 7 and q minus 7. Those are gone. Over here, 3q minus 4, 3q minus 4. Those are gone. And over here, I have both factors of the denominator being multiplied, so I actually lose that entire denominator. So let's write out again, what are we looking at? I have now 3q minus 4 times 3q minus 15 plus, this is q minus 7 times 4. Now you can write it in that order. I'm going to reverse it because that's just what we're used to seeing in math. And over here I have q squared plus 53. And I put it in parentheses to keep it clean, but those parentheses aren't doing anything at this point. So now what I need to do is actually multiply stuff out and look to combine like terms and solve. If I multiply 3q minus 4 by 3q minus 15, what I will get is 9q squared minus 12 minus 45 is minus 57q. Negative 4 times negative 15 is plus 60. And then I will have 4q minus 28. And over here I have q squared plus 53. All right, so let's combine our like terms. 9q squared minus 53q plus 32 is equal to q squared plus 53. Okay. And then again, it's a quadratic, so I know what I want. I want to get everything to one side. If I subtract q squared, I will then have 8q squared. There are no q terms on the other side. If I subtract 53 from 32, then I will end up getting negative 21. Okay, so I have 8q squared minus 53q minus 121. This is factorable. It might be a little bit intimidating to factor it, but it is definitely factorable. You could always try using quadratic formula, but if the numbers are too intimidating to factor, usually quadratic formula is going to be even worse. Because think about it, quadratic formula, you're going to have to square b. Anyone know what 53 squared is off the top of their head? Good, because neither do I. All right, let's actually factor this. 8 times negative 21 is negative 168. Now I need factors of negative 168q squared. You can make a table of values, and I made reference to this in an earlier video. The other thing you can do, if you go to your calculator, let's go to y equals. I'm going to clear out these things that I don't need anymore. And what do I have? I need factors of negative 168. So negative 168, or you can just do 168, divided by x. Then I'm going to go to the table. By doing this, what I see in the table is a table of the factors of 168. You can write them down as you wish, but we don't really need to do that. We know we need factors that have a difference of negative 53. Well, 1 and 168, that would be 167 is their difference. 2 and 84 would be 82. And I get some luck right off the bat. 3 and 56. If I did a negative 56 and a positive 53, that is what would give me negative 53. So I'm going to do that. So as I've just shown you, this calculator trick can be useful when you get something that actually has kind of horrendous numbers. I apologize, that's not supposed to be q squared. Negative 56q plus 3q minus 21. This is what I'm factoring. And then we factor as per usual. Group these, and I get 8q times q minus 7. Take out a 3 from the second group, and I'm left with q minus 7. Okay, so what factors do I have? This means I have q minus 7 and 8q plus 3. Alright, if I have q minus 7 and 8q plus 3, well then, that means from here I'll get q equals 7. So I can set q minus 7 equal to 0 and solve that very easily. Here I have to think about it a little bit more. 8q plus 3 is equal to 0. It means that 8q is equal to negative 3. It means that q is negative 3/8. So again, I have produced two solutions right here, 7 and negative 3/8. Now here's the ultimate question. We have yet to see an example of this. Are both of these solutions valid? Go way back to the top where you figured out that common denominator and figured out what your restrictions were. My common denominator was q minus 7, 3q minus 4, which gave me the restrictions that q could not equal 7, nor could it equal 4/3. Well, I didn't get 4/3, but I did get 7. So this is what we call extraneous. And it's not a valid solution. The only solution then is negative 3/8. Now you might ask yourself, well, if I tried to graph this with my calculator and solve by graphing, what would this extraneous solution do? There's generally speaking not an easy answer to this. I can tell you on this problem what it would have shown as is that both the left and right hand sides of our original equation would have had a vertical asymptote at x equals 7, because we'd be using x if we were using the calculator, which is not, again, something that we're interested in. What I want is values that make both sides equal to real numbers. If they make either side undefined, that's a problem. I hope this has been helpful to review solving rational equations. Again, if you understand them, they're ultimately not that difficult, barring very difficult equations. This one right here was a little bit cumbersome. It required some work, but I was very careful to make the numbers work out nicely. If I had just come up with one off the top of my head, we would have had to use our favorite thing, quadratic formula. And then there would have been even no guarantee that I would have gotten real solutions. But we're focused on real solutions, and for a rational equation, generally speaking, that's what you're going to get. Real solutions, or potentially no solution, not imaginary, and quadratics that are factorable. Again, I hope this has helped. If you have questions, please consult your textbook. Just kidding.